So I always appreciate the opportunity to introduce students, particularly students in the Institute who bring a fresh perspective and enthusiasm to the work. Today we have with us Nuoya Xiong, who is a second-year PhD machine learning student here at CMU, who works with Arti Singh, our Institute Director. He has an undergraduate degree from Tsinghua University and recently did a summer internship with Meta AI. His research interests are in foundations of decision-making and very interested in learning theory for decision-making. So his work is right here at home in AI-SDM. So really looking forward to your talk today on RLHF. Please join me in welcoming Nuoya.
Thanks for the introduction. I'm very excited to be here to give my talk. So this talk is about the multi-objective and multi-group RLHF. So this is a joint work with my advisor, Arti. So yeah, let's begin. So first, I will talk about some backgrounds. I believe many of you have used the chatbot. Actually, the chatbot asks you to choose the preferred response between two options. So this is a technique called reinforcement learning with human feedback. And this is frequently used in recent years for post-training stage of the large language model. So basically, the agent first tries to generate two responses and ask the user to choose one preferred response. So by receiving this preference feedback, actually, the agent can learn what's the human's preference and try to improve itself by aligning the human preference better. Yeah, so one question is that why do we need the alignment in recent years? So now you can actually, you can use the internet to find any open source large language model and you can download them and use them easily. So they can generate pretty decent answer, but these pre-trained models may not perform very well in many downstream tasks. For example, if the user asks the agent to summarize the main causes of climate change, so some pre-trained model, or we say the unaligned model, may respond like this. So climate change is driven by a combination of factors such as blah, blah. So it is correct, but the user may not feel good about this response because it is a little bit unstructured. So for example, the user may prefer some structured answer that can help them to list some points. So by receiving this preference feedback, actually, we can teach the agent to actively generate some response like this. So they can help the users to list some points, and it is very clear and organized. So people may feel much better about this response. So that's why we need the alignment process, or we say the post-training stage, or the fine-tuning of the large language model, because we want the pre-trained model to behave, to become aligned the human preference much better. Yeah. So if we talk about the alignment with the human, actually there's a lot of research about imitation learning, which is also try to align the behavior with the human. So in imitation learning, actually, if you want a robot to drive a car, how to teach it to drive a car, you can first ask a true human to drive this car and collect the data as the expert data, right? And then you feed this expert data to the agent and ask the agent to imitate the behavior pattern. And finally, the robot will generate some policy that is really similar to the human, and also it can perform very well in some downstream tasks. However, in recent years, people find that even if it's very successful in some scenarios like the automatic driving, but actually when you consider the text generation task in recent years, this framework actually does not work very well. The question is that you cannot ask the human to give you the trajectory feedback, which means the full response for the text generation, right? So imagine that how annoying it is if you ask the chatbot and the chatbot asks you to generate a response and for them to learn. So it is very annoying, right? So this means that the data is the pure problem and it is very hard for collecting the full response by the human. So in recent years, people find that okay, we cannot collect the trajectory feedback and apply the imitation learning. Then how about we let the agent to generate response and only ask the human to evaluate the response? So this is called the preference feedback. And it is relatively easier for human to give the accurate answer, right? Because it is much easier for you to evaluate two response rather than generate a new response. And also we can find that this kind of preference feedback also help us to infer the reward model of the human and also can help the model to improve themselves to generate some response that align the preference much better. Yeah, so this is why we need to consider the preference feedback. And now I will talk about what the alignment exactly looks like in the recent post-training stage. So assuming that we have a pre-trained language model, so this model is relatively good and it can generate a very decent answer, but it cannot align the human preference very well. So we also have many preference data that is collected from the user. So we want to use this preference data to improve our model. So how can we deal with this? The first step is to train a human reward model. So this reward model will receive a full response as the input and generate a scattered score. So the reward model should assign a higher score to the preferred response. That's the ideal reward model, right? So it can be a good proxy of the human implicit reward given the preference data. Yeah. So after we getting this reward model, we can then plug in any kind of reinforcement learning algorithms. So try to fine tune the pre-trained language model. For example, in this case, we want to maximize the expectation of the reward function. Yeah, but we also want to introduce the KL penalty term. So this is because we do not want our model to become overfitting to the reward model, right? So we don't want our model to be too far away from the base model. So otherwise it will lose the basic generation ability. So this KL penalty is also important. And yeah, and after that, there's also sometimes an online phase. So we use the new policy model to generate more prompt and give us more preference data. Yeah, so this is a brief introduction about the recent alignment process. So yeah, even if it's very popular and very useful in the recent years, however, we also find that there are some disadvantages of this framework. So the first disadvantage is that for the data collection, actually, it is relatively hard for humans to give the feedback on the general quality of the response. For example, if you are considering a travel plan, maybe you should consider the cost, the time, and whether it's comfortable and whether it's safe. And when you're trying to evaluate a paper, for example, you need to consider the fluency, the conciseness, and also whether the paper is correct. And also, if you are evaluating whether a model is good, you may want this model to be a harmless model, and also it will be helpful. And if the model is a little bit humorous, of course it's an extra bonus, right? So you have multiple factors when you when you collect the data in the real world. So it's very hard for humans to give the accurate feedback on the general quality of the response because it sometimes it is unclear. Right? Yeah, and also another disadvantage is also the general quality. So in the reward training phase, it's hard for a simple reward model to capture the general quality of the response because you want to use your reward model in the RL training loop. So you require it to be a small reward model. Otherwise, the RL training will be very slow, right? So if you are using a small reward model, actually, it is very hard to capture all of these factors in a very small, like 7B model, right? Yeah, so that's why one natural solution about how to deal with this general quality is that how can we decompose the general quality into different aspects. And for each aspect, we can use a different reward model, and we can also collect the data from only on one aspect, right? So that's why we need to consider something called the multi-objective RLHF. So for example, in the data collection phase, if we receive this preference data, so how should I take medication to recover faster from a cold? Then some response may like, so you can recover faster by taking higher doses of medication. So it is helpful, right? But it is also very dangerous. Sometimes it will cause the health problem. And another response we like, it's important to follow the instructions provided by the label. So it is very safe, but it's also not that useful because you ask the agent you want to receive some advice, right? So if we only ask the human which response do you prefer, the human may just answer, I'm unclear which one is better, right? Because both of them has the advantage and disadvantage. But if we change the question like which response is safer or which response is more helpful, then it is easier for human to give the accurate answer, right? They can say the second one is safer, of course, and the first one is more helpful. So it is relatively easier for human to give the accurate answer. And also, if you are training the language model, this kind of preference feedback is much more accurate. And it is also good for you for the training, right? Good. And for the reward training problem, in this case, we can train multiple rewards. For example, we can train a reward for helpfulness and train a reward for harmlessness. And then we can combine them and get a new reward. So the new reward is called our final, and it's the most easy way is the linear combination of the two reward models. And the weight, we can see that the weight is unknown or known, and it can be given by human, and it also can be identified by the preference data. Yeah, so this is the classical multi-objective RLHF, and yeah, it is very useful, but sometimes there are a lot of questions that need to discuss when you apply the multi-objective RLHF in the real world. So I will discuss 4 questions one by one. So let's begin. So the first question is that it seems that we need to retrain the whole model when the alpha 1 and alpha 2 is changed, right? So for example, if you think about this kind of formula, when you change the alpha 1 and alpha 2, actually you get an entire new reward, right? And you use this entire new reward to train a new model. So whenever the reward is changed, actually you need to retrain the whole model. So that is very computationally expensive, and we don't like it. So how can we deal with this problem? Actually, there's a lot of approaches that can deal with this problem in a very elegant way. So the first approach is called the model merging. So we can first train one, for example, in the harmless and helpfulness multi-objective data set. We can first train pi I for each objective I. So in this case, we train the harmless LM and train one helpful LM. And then we directly merge all the model's parameters to get the new model. So it does not need to train the whole model, right? Because when you change the weight, actually you only need to remerge the model. So it is very computationally friendly. And yeah, it is also a very popular area. And another approach recently is by combining the logics of different models, which is called the multi-objective decoding. So when you generate the next token, you first get the logics, which is the distribution of the next token. And then after you getting 2 logics from 2 models, you combine them and get a new logics. So you can use this new logics as the distribution to generate the next token. So it is also a very elegant solution, and empirically it performs very well in many downstream tasks. Yeah. So this the question 1, which is important, but it can be naturally solved by many previous approaches. So the second important question is that what if the weight is unknown? Actually, in the previous example, we always assume that the weight is given by the human, right? If you want to apply the model merging, you first need to know the weight. But how can we identify the weight if we don't know exactly the weight? What is the weight? So the solution is that we can actually try to identify the weight by the implicit importance of the human. So I will provide an example. So in the previous example, when you ask which response is safer or more helpful, and the human answers, the first one is safer. So what's the information you can get from this response? So first, you can directly know that the first one is better in safety, right? So this is a direct answer. But you can also receive some information that the user tends to notice the safety property rather than the helpful property, right? So which means that this user so the implicit importance of the safety property for this user is relatively higher, right? Yeah, so in order to model this kind of implicit importance, we use this formula. So the high-level explanation of this formula is that the probability for choosing one objective is related to both the reward gap and the importance weight. So it means that, for example, for the objective I, so if the user tends to notice the objective I, then either the weight of the user is high or the reward gap for the objective I is really relatively high, right? So if that makes sense.
Good question.
Yeah.
So can I understand? So for example, right now you are considering like two features, like helpness or safety.
Yeah.
And you are requiring to get the answer from human for both of them, ideally. Instead, like say previously, we only need the preference, which is one feature from human, like which I prefer. Now you need the human to say, okay, this one is safer and another one that's more helpful. Do I understand correctly?
Yeah, but there's a little difference. So we ask the human to choose one index and answer the question. So if, for example, in this case, the human only asks the first one is better in safety.
Okay, and for helpness, you also need that from other. Like,
yeah, from other users.
I see. Thank you.
Yeah, but in this case, we will find that if the user tends to answer the question by safe, so in terms of the safety, that means either the importance of this safety property is higher for this user, or the reward gap between two response for the safety is really big. So the user will tend to notify this property.
Like sometimes when an LLM like prompts me to choose between two responses, I would just sort of click on randomly, right? And so with like somebody answering this prompt, they might sort of read it and just choose to answer like the first part of it, right? And not like respond to helpfulness. So does this sort of account for whether people are like answering the full question or whether they're simply only mentioning safety because that's like the first thing they were asked about?
So if you mean the human, so human prefer to answer the safety property, that means the safety, actually the importance of the safety is much higher in the human's mind, right? Rather than the helpfulness.
But couldn't it also be that it was the first one mentioned, mentioned before helpfulness? So I was just wondering whether like you consider.
Yeah, you can also maybe change the order to eliminate this bias.
Okay.
Yeah. Yeah, there's a lot of bias in the question answering. Sometimes you just randomly choose one when you use the chatbot, and that's why we need the data to be clear and accurate. Yeah, and okay.
Maybe related. So, I mean, I guess you could run like the user study in principle where you ask people explicitly like which ones they find more important, and then they, like is this based on any kind of like experimental data, or is it just kind of like a model you put down?
Yeah, you can also ask the user to choose which one is important, but actually we want to just extract the information based on our based on the query.
Yeah, so if you did an explicit kind of thing, would it align with would your model align with that?
So can you repeat?
Like, you want to do a single query,
Yeah.
right? So you have this model for the
Yeah.
implicit probability.
Yeah.
But in principle, you could measure explicitly what this probability is. And I'm asking, have you done experiments on whether your model aligns with the ground truth?
Yeah, we don't run the true experiment about this, but so this is for how to identify the way theoretically, and we also this is actually an assumption about how the human chooses the index, but I think this is a reasonable assumption when you do run some experiment. I think the alpha, so we can try to identify the alpha I. Because it's a reasonable assumption, right? If the reward gap is relatively large, so then you tend to notice by this property, and also when the importance weight alpha is relatively large, you also tend to notice by this property. Right? And the third question is that so far we all consider the linear aggregation, but sometimes the linear aggregation is not the only way to aggregate the reward, right? So, and it sometimes does not represent what we like. For example, consider the following example. It's the previous one. So how should I take medication to recover faster? And when you receive this kind of response, actually you can find that it's helpful and it's not that harmless. So you may find that the reward model behaves like this. And if you only consider the linear aggregation, for example, 0.5 and 0.5, then it will state that this response is not that bad. So it is acceptable, we will see that, but it's actually a very bad response because it is very dangerous. So how can you deal with this problem? So sometimes people are studying that when you calculate the minimal value of the reward function, that's more like the fairness of the multiple reward models, right? So when you calculate the minimal reward models, minimal reward value, it actually equals to 0, and that tells you that this response is bad because it's too harmful, right? So I mean that calculating the minimum value of the reward function is also an important aggregation. And can we consider a general framework that can include both of these kind of important aggregations? So actually, sometimes we motivated by the social choice theory, and we find that the unique solution for aggregation that satisfies some actions in social choice theory are weighted p-norm aggregation. So it is a general extension of the linear aggregation, right? When the p equals to 1, actually the Rxy degenerates into the linear combination of the reward model. But when you change this p to minus infinity, actually the Rxy will be the minimal value of the reward model. So in fact, the p represents the degree of fairness we want to achieve, and we can adjust p based on our requirement. Yeah, and I also list some actions that is in the social choice theory. And if you are interested in these actions, you can feel free to check some paper about social choice theory. And in a high level, these actions are very intuitive, something like the weighted symmetry or the independence of common scale. Yeah, it's very intuitive. So the question now is that we provide a nonlinear aggregation approach, but how can we deal with this nonlinear approach? So our key idea is to transfer this nonlinear aggregation maximization problem into another problem, because we noticed that theoretically is generally a hard problem. So we find that we can transfer this problem into another problem that can be solved in an elegant way. So the key idea is called the target set. So the definition of the target set is generally a convex set, but it is defined by the following formula. And for example, if you are given the alpha and P and C, then the WPC alpha will be the set of all points that the weighted p-norm aggregation is larger than some threshold C. Right. Yeah, so P, in this case, P is less than 1, so make sure that the W star is a convex set. Is that clear? And also, we can also define the current reward vector. And so the current reward vector also contains a regularized term. And the element, for example, the ith element of S pi represents the expectation of the reward for objective I, and also with some regularized term. Yeah. So in this case, our goal is to find a policy pi such that the S pi is in the W star. So what does it mean? So when the S pi is in W star, actually the current policy, if you consider the pi as your current policy model, then that means the aggregation of the current reward is larger than some threshold, right? So that means maybe the user will be satisfied by this kind of model because the weighted p-norm aggregation is large enough. And now we also, given this goal, our objective is defined by minimizing the distance between the current reward vector and the W star, which is the target set. Yeah, so we transfer the general nonlinear aggregation maximization problem into another problem. So this problem is very similar and it can be solved in an elegant way. Yeah, I will talk about the algorithms later. But before we introduce our algorithm, we also have another question, the last question. So in this case, what if there is a preference conflict? So when you receive the preference data set, if you receive A is better than B and B is better than A, so how can you deal with this problem? So you may think that this is because you collect the preference data from multiple group of users, right? And for one group, maybe they preferred A, and for another group, maybe they preferred B. So you will receive some preference conflict. So how can you deal with this problem? The first step is to split the preference data set into different groups. So it can be implemented by any clustering algorithms, and it is also studied in previous paper. Yeah, but the thing is that how can we deal with this problem even if we split the data set into different groups? How can we achieve the balance between multiple groups and satisfy all of them? Yeah, so we find that given our formulation of the target set, actually there's a very natural solution for the multiple group problem. For example, if we have k groups and each group k has a different weight alpha k and different aggregation parameter pk and also different requirement ck, and then we can achieve the consensus of the multiple group, which is the intersection of all the groups target set. Right. For example, in the right figure, you can see that we have 3 groups, but after we have 3 groups and split them, we find that we can use the final target set as the intersection of all the 3 target sets. Yeah, and there's also another way to achieve the balance between multiple groups. We can use another weighted Q-norm aggregation. But the aggregation is applied on the distance between the current reward vector S pi and the target set for the group K. Right? So in our framework, we actually solve this kind of 2 problems in one general framework. And I will talk about the algorithms later. So do you have any question about all these 4 questions, all of the questions before?
Yeah, thank you. Can we just use the aggregated reward to train RLHF?
Yeah, we find that the aggregate reward, this is also a very popular approach. But the thing is that even if we can normalize the reward and the expectation of the reward is positive, we can make sure that it's relatively positive. But sometimes you will encounter that for one response, one reward is negative. So in this case, we run some experiment and find that actually it will lead a very unstable performance for the algorithms you provided.
So you're saying, for your approach, you're going to balance the minimum of rewards. What do you mean?
No, I mean, so you mean that you just aggregate the reward directly and use some reinforcement learning algorithms to optimize it?
Using the aggregated reward introduced by your previous formula.
Yeah, so
the p-norm aggregation, right?
Yeah, so you aggregate in and use some reinforcement learning algorithm to optimize it, right? So the thing is that even if we can normalize the reward, but sometimes in the real world, the reward function have a very large variance, and sometimes for one response, the negative will be negative, for example. In this case, the weighted p-norm aggregation does not make any sense. So it will lead to a very unstable performance if you just aggregate them and directly training it.
I think you're saying there is an outlier of
Yeah.
rewards, so the advantage will be very dispersed, so the training is being played out.
Yeah, even if you can sometimes make sure that the expectation of the reward is relatively positive.
How do you decide little c for different groups?
So
The little c.
little c. So this c, we consider this c as the requirement for multiple groups, and we assume that it's given by the human. Yeah. Okay. But before I introduce the algorithm, do you have any question about the previous talk? Yeah. So I will briefly introduce our algorithm for this general framework. So basically, at each round, if we can get the current policy model, which is pi t, and then the first step is to calculate the current reward vector vt, and then you can actually calculate the projection of the vt on the target set wt. So notice that because we don't know the reward function exactly, so the wt is also estimated. So based on the preference data you received, so it is also changed over time. And after that, you can calculate the direction which is defined as dt, and project all the reward on this direction. So then you can actually maximize the inner product of the dt and head r, right? So in this case, actually, we motivated by the Blackwell approachability for our theoretical analyze. Actually, you can decompose the whole problem into a sequence of sub-problems, and each sub-problem is actually a linear aggregation maximization problem, right? Because at each round, after you calculate the direction dt and you project the reward on this direction, then it becomes a linear aggregation maximization problem. So that means you can use any previous oracle to to optimize this direction. Do you have any question about what the high level of the algorithms? Yeah, so because we also consider the multi-group problem. So for the constant, if we consider the consensus of the multiple groups, then the target set will be generally a convex set. But also, if we consider the Milford minimization problem, then we will have different target set, and our projection direction will be calculated by the weighted combination of all these projections. So So for theoretical results, we find that under standard assumptions with high probability, our policy actually can achieve the optimal policy that can give us the smallest possible distance to the target set. And also, if there is a policy, optimal policy that S pi is in W star, then we can guarantee that our policy, our algorithm also can give us a policy that's in W star. Yeah, and also for the Milford minimization problem, we can find that our regret is also dependent on the degree, the Q, which is the degree for aggregation in the Milford function minimization problem. So for the empirical results, actually we use the distance to the target set as our metric, and we compare many baselines. So RS and MOD are two popular linear aggregation baselines, and also we implement the AR, which is what we mentioned before. So it's the reward based on nonlinear aggregation. We first calculate the reward and aggregate them and use some RL algorithms to optimize it. And we find that actually our algorithm can achieve the best performance, while the AR is also designed for the nonlinear aggregation, but it is really unstable because there are some outliers in the data set. Yeah, and also even if our algorithm is a general framework, when we apply the max-min set, when we apply our algorithm to the max-min setting in which we want to maximize the minimal reward across multiple reward value, we find that our algorithms also achieve a comparable performance compared to the previous max-min RLHF algorithms, which is particularly designed to solve to maximize the minimal value of the reward. Yeah. So we mentioned that even if our algorithms is a general framework, but when you apply to some previous setting, actually it also performs not bad. Yeah, and there are also some empirical results for multi-group setting, and yeah, if you are happy to read about it, you can check our paper. So I will talk about some future directions about this kind of areas. So there are some interesting questions about this work and also in this relative area. So while our current framework focuses on how to align the model behaviors with multiple groups of human preference, but the real problem is that in the real world, the clustering algorithm may not work very well if you consider very complex scenarios. If you contain multiple groups, it will not work very well. So it is also useful if you can study how to just aggregate the preference instead of first split the data set to different groups and aggregate the reward. So how to directly aggregate the preference is also a very interesting question. And the second question is that even if we can identify the importance weight of the human, but actually the degree of the aggregation P and the threshold C, we need to receive this information from the human. So can we just identify this parameter in the preference data? And I believe there are some papers about how to learn the parameter P based on the preference data, and how can we apply it to the real world. And the last thing is that our work is also very similar to areas that encourage multiple LMs to collaborate and debate with each other to generate a new response. But the difference is that in multi-objective RL, actually some objectives are conflict. So it is much harder to build a multi-agent system that can generate a relatively strong model. Because when you build a multi-agent system in many papers, they just focus on the math, the coding, and something like instruction following. So you can expect that there are some models that can perform really good for all of these objectives. But when you consider the multi-objective RL, you may think that the two objectives may be conflict, so it is impossible for one model to generate a very good answer generally. So it is also interesting how to enable a multi-agent system to actually generate a better response that can both improve the helpfulness and harmless, but it's much more challenging than the classical multi-agent system. Yeah, so that's all about this talk. So feel free to ask some question.